Introduction to the Beeman algorithm. The Beeman algorithm is a numerical technique used to integrate differential equations, which are commonly encountered in fields such as molecular dynamics and astrophysics. It is a variation of the Verlet algorithm, which is widely used for simulating the motion of particles and celestial bodies. The Beeman algorithm provides a more accurate and stable method for simulating complex dynamical systems, making it an essential tool for researchers in various scientific and engineering disciplines. Predictive integration. The Beeman algorithm is based on predictive integration, which involves extrapolating future states of the system based on its present and past states. This method is particularly useful when dealing with complex interactions where analytical solutions are not available. The algorithm excels at predicting future particle positions, velocities, and accelerations, providing a crucial basis for simulating the evolution of dynamic systems. Place prediction. The Beeman algorithm's ability to predict future particle positions is a significant advantage over other integration methods. By considering not only present velocities and accelerations but also earlier accelerations, the algorithm achieves higher accuracy in comparison to simpler integration strategies. This enhanced precision is especially valuable in molecular dynamics simulations, where exact atomic positions are crucial for understanding molecular interactions and predicting conformational changes. Velocity calculation. Correct velocity prediction is intrinsically linked to position prediction. The Beeman algorithm provides a strong method for determining velocities, ensuring consistency between position and momentum over time. This close coupling of position and velocity calculations contributes to the algorithm's overall stability, preventing unrealistic or erratic behavior in simulations. Time dependence. The predictive nature of the Beeman algorithm depends on the concept of discrete time steps. The algorithm calculates future states at fixed intervals, making a step-by-step evolution of the system. The selection of time steps significantly influences the accuracy and stability of the simulation, with smaller time steps typically resulting in more accurate outcomes but requiring greater computational resources. Error management. While the Beeman algorithm provides good stability, inherent errors related to any numerical integration technique can accumulate over time. Cautious consideration of time step dimension and system properties is essential for minimizing these errors and ensuring dependable simulations. Advanced strategies like adaptive time stepping can further improve the algorithm's accuracy and efficiency. Enhanced stability. Numerical stability is paramount for dependable computational simulations. The Beeman algorithm provides enhanced stability in comparison to simpler integration methods, making it suitable for modeling complex systems over prolonged durations. This attribute is essential for acquiring correct and significant outcomes, particularly in situations involving multiple interacting particles or lengthy simulation instances. Error propagation management. The Beeman algorithm's design inherently mitigates error propagation. Its use of earlier acceleration knowledge helps dampen the buildup of numerical errors over time, resulting in more stable trajectories. This characteristic is particularly relevant in long-duration simulations where error accumulation can significantly influence the accuracy of predictions. Power conservation. While not completely energy-conserving, the Beeman algorithm reveals good power conservation properties. This contributes to its stability by preventing artificial power drifts that may result in unrealistic behaviors. In astrophysical simulations, this ensures that planetary orbits remain stable over simulated millennia, reflecting the observed long-term stability of actual planetary techniques. Time step tolerance. The Beeman algorithm demonstrates a relatively high tolerance for larger time steps compared to other integrators. This results in significant computational savings without compromising stability, allowing for efficient simulations of complex systems. For example, in materials science simulations, larger time steps can be employed to model crack propagation or materials deformation, reducing computational overhead without sacrificing accuracy. Symplectic conduct. Although not strictly symplectic, the Beeman algorithm reveals some symplectic-like traits. This property contributes to its long-term stability by preserving certain geometric invariants of the simulated system. In simulations of Hamiltonian systems, this may be essential for sustaining the qualitative correctness of the outcomes over prolonged integration durations. Sensible purposes. The sensible utility of the Beeman algorithm stems from its ability to precisely and effectively simulate complex dynamic systems. This translates into a variety of functions throughout numerous scientific and engineering disciplines. A crucial connection lies in the algorithm's capability to model techniques ruled by classical mechanics, making it suitable for issues involving particle interactions and trajectory predictions. Applications. The Beeman algorithm has been successfully applied in various fields, including molecular dynamics, simulating the movement of atoms inside proteins, understanding protein folding, and predicting conformational changes. Astrophysics, modeling the evolution of celestial bodies, predicting planetary orbits, and analyzing the long-term stability of star systems. Materials science, simulating the behavior of materials under stress, predicting crack propagation, and optimizing materials' properties. Computational chemistry, simulating chemical reactions, predicting response mechanisms, and optimizing chemical processes. Enhanced stability and sensible purposes. The Beeman algorithm's enhanced stability and sensible purposes make it an essential tool for researchers in various scientific and engineering disciplines. Its ability to manage error propagation, preserve power, tolerate larger time steps, and exhibit symplectic-like traits makes it a strong alternative for simulations involving intricate systems or requiring long-term predictions. Conclusion. In conclusion, the Beeman algorithm is a robust numerical integration technique that provides enhanced stability and sensible purposes for simulating complex dynamic systems. Its ability to manage error propagation, preserve power, and tolerate larger time steps makes it an essential tool for researchers in various scientific and engineering disciplines. As computational capabilities continue to advance, the Beeman algorithm will remain a valuable device for simulating intricate phenomena and enabling more accurate and efficient simulations. Commonly requested questions. This section addresses frequently asked questions related to the Beeman algorithm and its implementation in computational instruments. Query 1. How does the Beeman algorithm differ from the Verlet algorithm? The Beeman algorithm provides improved accuracy in velocity calculations and exhibits better power conservation properties compared to the Verlet algorithm. Query 2. What are the key benefits of using the Beeman algorithm? The key benefits include enhanced numerical stability, better power conservation, and improved accuracy in predicting particle trajectories, particularly velocities. Query 3. What are the limitations of the Beeman algorithm? The Beeman algorithm, like any numerical technique, is not without limitations. It is not completely energy conserving, and its accuracy depends on the chosen time step. Query 4. How does the time step affect the accuracy and stability of Beeman calculations? The time step is a critical parameter. Smaller time steps typically result in higher accuracy but require greater computational resources. Larger time steps can compromise accuracy and potentially lead to instability. Query 5. In what scientific fields is the Beeman algorithm commonly used? The Beeman algorithm is commonly used in molecular dynamics, astrophysics, material science, and computational chemistry. Query 6. How does one select between the Beeman algorithm and other numerical integrators? The selection depends on the specific application and desired balance between accuracy, stability, and computational efficiency. The Beeman algorithm is a robust alternative when good accuracy and stability are required, but it may not be optimal for all situations. Ideas for efficient utilization of Beeman-based computational instruments. Optimizing the use of computational instruments based on the Beeman algorithm requires careful consideration of several key components. The following tips provide guidance for attaining accurate and efficient simulations. Time step choice. The combination of time steps significantly impacts both accuracy and stability. Smaller time steps typically yield higher accuracy but require greater computational resources. A balance must be struck. System initialization. Correct initial conditions are essential. Errors in initial positions and velocities can propagate throughout the simulation, affecting the reliability of outcomes. Cautious validation of initial conditions is necessary. Periodic boundary conditions. When simulating bulk materials or large systems, periodic boundary conditions are sometimes employed. Correct implementation and validation of these boundary conditions are crucial for avoiding artifacts and ensuring correct representation of the system. Thermostatting and barostatting. For simulations requiring fixed temperature or stress, appropriate thermostatting and barostatting algorithms must be used along with the Beeman integrator. Cautious choice and parameterization of these algorithms are necessary for sustaining desired thermodynamic conditions. Drive force validation. The accuracy of any molecular dynamics simulation, including those using the Beeman algorithm, relies on the chosen drive force. Applicable validation and parameterization of the drive force are essential for acquiring dependable outcomes. Knowledge evaluation and visualization. Efficient knowledge evaluation and visualization are crucial for extracting meaningful insights from Beeman simulations. Tools for visualizing trajectories, calculating statistical properties, and analyzing power fluctuations can provide valuable information. Efficiency optimization. For large-scale simulations, computational efficiency is essential. Optimization strategies such as parallelization and code optimization can significantly reduce simulation time and enable the simulation of larger and more complex systems. By adhering to these suggestions, researchers can significantly improve the accuracy, efficiency, and reliability of simulations performed using Beeman-based computational instruments. By carefully considering these components, researchers can maximize the potential of the Beeman algorithm for gaining valuable insights into complex dynamic systems.